Do you remember the first time you saw a magic trick? That may have been your uncle making a coin appear from behind your ears, or a really silly trick like this. I love magic, and I've spent most of my life dedicated to this weird world of illusion and deception. In the first part of my life, I simply used magic to entertain people. However, for the last 15 years or so, I've been using magic as a way of uncovering the secrets of the human mind, and I'm the director of the Magic Lab at Goldsmiths, and we use magic as a way of exploring the human mind. We study misdirection and mind control techniques to learn more about consciousness and the illusion of free will. We try and apply a lot of this knowledge to the real world as well. So at the moment, we are teaching robots and artificial intelligence bots to perform magic tricks so that we can learn more about what happens when machines start to deceive us. Now, I know this sounds very scary, and it may reduce the time that we're spending on this planet, but don't worry, we also use magic as a way of enhancing people's well-being, and we're using it to make people feel better about themselves. So at least if we all die very happily. So what I'd like to do tonight is give you a bit of an insight into this world of art and science and technology, and give you a bit of an illustration of how we use magic as a way of exploring the human mind. But as we're talking about magic, who would like to see some magic? Yeah? I know this is all sciencey, but I thought I can't really do this talk without actually performing a bit of magic. So I'd like to show you the illusion that I first experienced, and that really got me into magic, which is known as the cut and restored rope. The idea is really very simple. I have a piece of rope and a pair of scissors. And the idea is to cut the rope in half, once like so, leaving you with two identical pieces of rope. Kind of similar pieces of rope. You know, you take the short. You know, I'll show you something different, okay? Now, did you know that if you got a piece of rope and you remove these two pieces, that actually you end up with a rope with no beginning and no end? But of course, there's not really that much I can do with this, so let me just take these and let's start again, okay? So, as I said before, this is called the cut and restored rope. The idea is really simple. You cut the rope in half once, twice. It really doesn't matter how many times you cut it. You take one of these ropes, stick it in top, et voila, the rope is restored. Thank you. Now, this is not all just entertainment. A bit of quiz. I saw lots of maths puzzles here as well. If I cut the rope up here and one more time down here, how many pieces of rope do I end up with? 1, 2, 3. You want to count? Yeah? Okay, got 1, 2, 3 equal length of rope. Now watch very carefully, because if I take the magic dust from the right side, not from the left, but from the right, sprinkle it over these ropes, watch what happens. I end up with a short piece of rope, a medium length rope, and a long piece of rope. As I said before, it's very important to take the magic dust from the right side rather than from the left, because if you take it from the left and sprinkle it over these ropes, they all become of equal length again. Thank you. Now, of course, I know it may look like I've got supernatural powers, but I don't, okay? I'm using psychological tricks to manipulate your mind. And the kind of illusions that you experience when you're watching a magic trick aren't that different to the kind of illusions that you experience in everyday life. It's just most of the time you're completely oblivious to these illusions. And as a magician, all I'm really doing is I'm using tricks and deception to point out this discrepancy between this illusion and your reality. And to do so, I often lie as well. So right at the beginning, you all thought I messed up this trick. That was a lie, okay? I've done this trick thousands of times. I knew exactly what's going to happen. That was just deception. And before I said it's important to take the magic dust from the right side, that was a lie as well, because of course the dust from the left works just as well. And even now, as I'm telling you, I've got 3 equal lengths of rope. Well, that's a lie as well, because in actual fact, one of these is short, this one here is medium, and this one right over here is a long piece of rope. Thank you. So, I work at Goldsmiths. I'm the director of the Magic Lab. And in the Magic Lab, we try and use magic as a way of studying the human brain, because magicians have developed very powerful techniques that allow them to manipulate your experience, and they can hijack your brain. And by understanding some of these principles, we can learn a lot about how the brain works. And so as a scientist, I'm interested in both the techniques that magicians use, as well as the experience that magic elicits. And so what is magic? Well, I think of magic as a mental state that creates a conflict in our minds. It creates a conflict between the things that you believe to be possible and the things that you just experienced. So you all know that it's impossible to simply cut a rope in half and restore it, and yet, of course, that's exactly what you've just experienced. Now, about 10 years ago, with a colleague of mine, Ben Paris, we started one of the first neuroscientific investigations into the science of magic by scanning people's brains whilst they were watching different types of magic tricks. And so we used an fMRI scanner, which allows us to identify brain areas that are particularly activated when you're doing different tasks or you're having different thoughts. And we try to identify the areas that are responsible for your ability to experience magic. And the results were truly surprising, because what we found was we got activation in two areas in the brain, one known as the dorsolateral prefrontal cortex, and the other one known as the ACC. What's really interesting about this is that these are areas that are generally involved when we experience conflict. So you're constantly experiencing conflict. Right at this point in time, you might want to listen to me talking, and there's all this music blasting around, which is also capturing your attention. So that creates a conflict between what you're wanting to do and what your attentional system is wanting to do. And these kinds of conflicts actually activate exactly the same kinds of areas. And so what this tells us is that magic really is about this conflict in beliefs, a conflict between the things that you experience and the things that you believe to be possible. So how can we create this conflict? Because as I said before, I don't have supernatural powers. Well, the way that we can do this is by using very surprising and often counterintuitive tricks. And so let me explain some of these tricks. Now, how many of you got one of these little pieces of papers? Yeah, most of you? How many of you would like to make a rabbit disappear? Okay, I'm going to show you one of the most amazing illusions, one of the most amazing magic tricks, and you're all going to learn this. So we're all going to make a rabbit disappear. If you do have one of these pieces of paper, what I'd like you to do is hold it out in front of you with this side. Close one eye, close your left eye, and then keep your eye on that cross. Okay, keep your eye on the cross, and then bring the piece of paper without moving your eyes slightly closer. Move it around until that rabbit disappears. Don't move your eyes. For me, if I'm looking at the cross, it's gone. Okay. Now, as soon as you move your eyes again, the rabbit will come back. If you move it further, it'll come back. If you move it closer, the rabbit comes back. Have you all experienced that illusion? Amazing, isn't it? Who's disappointed? Well, I know the trick itself is slightly disappointing, but the explanation is absolutely mind-blowing. Let's see why this works. And to learn about this illusion, we need to understand how the visual system works. Got a diagram of the eye here. This is a very quick lesson in perception. You've got an object, the scientist out in the world. If you want to perceive him, the light from the world is projected through the lens onto the back of our eyes, which is known as the retina, which is covered in thousands of little photoreceptors that encode all of the information and send it back through the optic nerve to different parts of the brain. The human eye is one of the most amazing organs, but there's a big design flaw. Can anyone spot it? It's the optic nerve. The optic nerve back here, so this is the junction. We've gone through a very weird evolutionary path, which means that we've got a massive gap on our retina. Of course, what this means is that we're not encoding any visual information, and so any information that falls on that area is gone. And the reason why that rabbit disappeared is once information is projected onto that blind spot, you simply won't be able to see it. But I promised a miracle, and here's the miracle. I've shown you the illusion. I've explained why it happens. How many of you noticing it? We simply don't. We're oblivious to the blind spot. You know it's there, it's big, it's about that big, it almost covers my fist out here, and yet we don't see it. But the blind spot is only one of many of these holes. Let me illustrate another one. How many of you ever noticed your eyes move? Have you ever seen your eyes move? Not on film, but your own eye movements. You can't. And the reason why you can't see your eyes move is because the visual system shuts down for about 100 milliseconds, so about 1/10 of a second, during each of these eye movements. This is a process known as saccadic suppression. And if you don't believe me, go to the toilet, stand in front of the mirror, look from left to right and try and spot your eyes. If you can, send me an email, I'll send you 1,000 quid. You simply can't. And that makes a lot of sense because, of course, if you try to take a picture with a moving camera, well, you get a blurred image and that information would be pretty much useless. And so we shut down about 1/10 of a second during each of these eye movements. But I hear you all say, well, surely, well, it doesn't really matter. Think again. Let's do a bit of maths. So our visual system is blind for about 100 milliseconds per eye movement. We move our eyes about 3 times per second, which means we make about 150,000 eye movements per day. What this means is that every day you are blind for 4 hours. A quarter of your daily life. And yet, we are oblivious to this darkness. Isn't that amazing? A quarter of our life, we are in darkness, and yet we don't notice it. These are all very interesting examples, but they're not that great for magicians. I mean, if I could get a rabbit and say, okay, keep an eye on here, and I'll move it to the blind spots, and I could probably make that rabbit disappear, but it'd be a really rubbish trick. But don't worry, there's loads of other tricks that are much more useful. Because as I'm looking around this room, I feel like I'm aware of most of the things that are going on around me. I mean, how many of you are good observers? Have we got any really good observers in the audience? Really observant people. Really rubbish observers? Talking to scientists, you're just a bit more realistic about the general population. But my intuition is that I'm kind of aware of most of the things that are going on around me, and yet this, again, is a massive illusion. And I'm going to illustrate this illusion to you. This is a picture that I took at the Royal Society. Well, I didn't take it, I took it off their website. How many of you spot the difference? Anybody, all of you spot the difference? So you get 2 pictures next to each other, there's a slight difference, and you have to point out the difference. We're going to play spot the difference, but rather than presenting the pictures next to each other, I'm going to switch between the images. And all you need to do is find the difference. But don't shout it out, okay? You'll ruin the trick if you shout it out. Once you've spotted the difference, hold up your hand. This should be very simple. Let's see. You can see a few hands, but most of the hands are still down. A few hands. We've got about a 1/3. We're not even halfway there yet. This should be really simple. Anybody who hasn't seen it, check out the picture up here. Very obvious, blatantly obvious, and yet you don't see it. This is a phenomenon known as change blindness, and what it illustrates is that although our intuition of the world is one of full sensory detail, the actual representation that we have of the world is much more impoverished. And you don't see these kind of changes because you're not attending to them. If we do the same thing here without the flicker, it becomes very obvious. You can see now it's very obvious that the picture has changed. And the reason why it's so obvious is because now you are attending to it. But unless you're attending to something, you simply won't see it. Now again, I can hear you all say, well, this is rather artificial. This would never happen in the real world. Think again. This is a lovely study that was carried out by Levin and Simons back in the 90s on an American campus. And what you'll see here is a video clip of the experimenter. He's the guy wearing the hard hat, asking the participant for instructions. They're having a chat. She's clearly looking at the person. And yet, she fails to notice that they're talking to someone else. Some of you may think this can only happen in America. It doesn't. We carried out studies at Spitalfield Market where is a PhD student of mine, and he changed the person for a mannequin. Most people did not notice that they were talking to a mannequin. And so intuitively we think that we are aware of our surroundings, and yet that is a massive illusion, and that's an illusion that magicians exploit. So how do we scientists test this? Well, to do so, I'm going to give you a quick demonstration. I'm hoping, this is a very big room, so I'm hoping that this is going to work. Can you all see the table here? Maybe kind of like right at the back. You might not be able to see this. I'm going to try and do this as obviously as possible. Really big. A quick trick. It's not long. Very, very quick. So just watch. Gone. How many of you did not see how the lighter disappeared? Most of you. Do you want to see it again? Have you got another lighter? No, I've got another one here. It looks really very similar to the one I've just used. I'm going to do exactly the same thing again. Can you hear that laughter? That ah? Remember that. Keep that in mind. Did you all see it? I just dropped it. This is not a real magic trick. We use these kind of things to study misdirection in the lab. And what I'm doing is I'm using misdirection to manipulate what you see and what you miss. So I'm using lots of different cues. So we've got this bright light here, which will capture your attention. I'm then using movement. So this is my hand moving to, again, drag your attention over here. This is the point at which I'm going to drop it. So I'm using lots of different cues. My gaze, so where I'm looking, is very important. We've got the sound from my snapping. The movement, these are all cues that will automatically capture your attention and prevent you from seeing the lighter being dropped. Now, what's interesting about this is that intuitively you think, well, surely you should be able to see this. And yet, of course, we don't. And at the beginning, I told you that magic is about exploiting this cognitive conflict. The conflict between what you believe to be possible, namely you should be able to see things, and the things that you've just experienced. Now, of course, we don't just do this kind of stuff for fun. There's a serious side to this. And we study this in the lab using eye tracking. And I'm going to try something that I'm probably really foolish to do here, is to do a little live eye tracking experiment. To give you a bit of an insight into how we can study this. So for this, I'm going to need a volunteer. Would you mind helping me out? Yeah? Please give me a big hand of applause. What is your name? Daniel. Daniel. When magicians say they're doing an experiment and they're not sure whether it works, they lie, because it always works. This here truly is an experiment. Daniel, could you just stand here? So what I brought along here is an eye tracker. This is literally just a headset that you can wear like a pair of glasses. Just put this on your head like a pair of glasses. Brilliant.
How do I look?
Yeah, you look fantastic. You look great. Doesn't it look great? Now, we've got two cameras on this tracker. So one camera here, which is going to film what Daniel is looking at. And then we've got another camera here, which is filming your eyes. So we can see, oops. Can we just switch? Let me just, sorry, you couldn't actually see any of this, could you? Let me just switch the computer around. So now up here, you can see this is what Daniel is actually looking at. And if we toggle along here, we can see his eye. So this is Daniel's eye. So if I can just come over here a bit, I'm just going to readjust this. Again, as I said, just look straight ahead. I don't know if this is going to work, but what you can see now is the eye tracker is locking on to Daniel's pupil, and the algorithm works out the center of the pupil, and by doing so, we can work out the rotation of the eye inside Daniel's eye socket. Now, the rotation is kind of interesting, but I'm really interested in where Daniel is looking. So to do so, we need to calibrate his eye position to a physical location in space. Daniel, can you just move your head down? Do you mind if, yeah, like that? You might like that, so we've got the screen. So what I'm going to do now is I'm going to bring up some calibration points, and we are calibrating Daniel's eye position to different locations in space. That is working so far. I'm amazed that's working. Daniel, can you look at me?
Turn my head?
Yeah, you can turn your head now. And now, can you see that little red dot? Very faintly. The lighting is terrible to do eye tracking in here. Can you just about see it? Daniel, look. A bit of a light dot. So that will now be tracking Daniel's eye movements. And I can now do magic tricks, and I can try and understand really how the misdirection works. So there, we got his eye position coming up. Can you see the little red dot? That's where Daniel is looking, or approximately. We do this much more carefully in the lab, but that gives you a bit of an insight into how we study these kinds of things. Thank you very much, Daniel. That's great.
God save you.
Thank you very much. Now, of course, this is all fun and interesting, but there's a serious side to this. So a lot of the research that we've been doing using eye tracking and misdirection has illustrated that people can miss something even if they're actually looking at it. So quite often, people will actually be looking at the light being dropped, and yet they clearly don't see it. And what a lot of this research is now telling us is that actually what you're seeing is not necessarily related to where you're looking, but where you're attending with your mind. And this has got serious implications. So think about driving. Driving is this really weird thing where you have to do all of these difficult things at the same time. And a lot of the research has shown that driving whilst talking to someone on a mobile phone is very, very dangerous. And there's a good reason for this, because your mind is being distracted. And in the UK at the moment, we're banned from using a mobile phone whilst driving, which is a good idea, because actually driving with a mobile phone is just as dangerous as driving whilst being legally drunk. But what about hands-free set? Well, intuitively, it will make sense that it's okay to drive with a hands-free set because you're looking at the right place. But what this research is telling us is that even if you're looking at something, you don't necessarily see it if you're being distracted. And that's why talking to someone on a mobile phone, even if it's a hands-free set, is just as dangerous. In fact, there's no difference between talking to someone on a hands-free set as there is on a handheld set. But of course, these things are very counterintuitive. They're surprising. Like there's no way I would get into a car after having drunk a few pints of beer. And yet, I'm so reluctant to stop using my mobile phone. And the reason for this is that we're generally oblivious to all of these limitations. And so by learning about these limitations, we can hopefully enhance kind of like new technologies, but also adapt our behavior. So I can see that you're all a little bit down by now, but I'm going to bring you even further down, because what I've illustrated so far is that you've got all of these black holes, all of these gaps in your experience. But what about the things that you do see? Can you trust your eyes? I'm going to argue no. Have a look at this image. What do you see? A duck, a rabbit. Some of you will have a duck, some of you a rabbit, and it may kind of like switch in between. This is a form of images which is known as bistable images. So you can either you see a duck or you see a rabbit, but you never see the two at the same time. It's a very interesting illusion because, of course, the physical world isn't changing. Your experience of what you are seeing is changing, but the physical world isn't changing. It's a static image. And what this illustrates is that your experience of the world isn't necessarily only related to what you're actually looking at, but it's how your brain interprets that information, because vision involves lots of complex computations. But what this means is that we can play around with your vision, and I can fool your visual system. Have a look at these two tables. Which of these tables looks wider, the one on the left or the one on the right? The one on the right looks a lot wider. In actual fact, the surface areas are identical, and I can illustrate this by removing some of the context and rotating them, and you can see that they're exactly the same. Once I add the context, you will see that they are very different. And so even if you know they're the same, your brain still interprets them as being different because you're using your knowledge about perspectives. What about this? You'll remember this image? An image that almost broke the internet. Some people see the stripes as black, others as gold. It divided the nation like Brexit did. Most people thought this was very surprising, because how could a simple property such as color be influenced by your brain? Surely we should all be able to see the same color. Well, that's because even color perception, something as simple as color perception, relies on you interpreting the information. Now, if this is the Brexit illusion, I'm going to try and show you an illusion by Bo Lotto, which will hopefully bring the country back together again. This is a cube, a color cube. What's the color of this square down here? Orange. What about the one up here? Brown. They look very different. Can you all agree on this? Yeah, all agree on it, but you're all wrong, okay? And I'm going to illustrate this by removing some of the context. All I'm doing is I'm just masking parts of the image, and you can see that they're exactly the same. Physically, they are the same, and yet you can experience them very differently. I will add the context again, even though you know they are the same. I've not changed the image. You're experiencing them as being completely different. Isn't that amazing? But are you ready for the illusion that is truly going to fry your brains? Yeah? This is the one that keeps me awake at night. And again, I'm going to illustrate this with a magic trick. Watch. Well, this is an illusion I have studied for about 10 years or so, using eye tracking and lots of other techniques. And it's one of my favorite illusions because it's so fascinating. The way it's done, again, it's not really a great magic trick. I'll just throw the ball up in the air a few times, and then I'll simply pretend to throw the ball when it's actually held in here. But what's interesting about this illusion is that about 2/3 of people actually experience on the final throw a ball is moving up and then disappearing somewhere up here. How many of you got that impression? Yeah, quite a few of you. And so this is an illusion where you're seeing something that clearly hasn't happened. Now, as with a lot of these tricks, the explanation of why they work is far more mind-blowing than the tricks themselves. And this one will truly fry your brains. Because what if I told you, I can see the future? You probably think I'm nuts. Yeah? What if I told you that you can see the future? You probably think I'm even more nuts. And yet, that's truly the case. Let me explain. And again, to understand this, we need to have a look at how the visual system works. For me to be able to perceive the world, I first need to encode the information through my eyes. We've looked at this process already. And then the information from the eyes is transmitted through different neural centers and different neurons to different parts of the visual brain that's responsible for all of the vision perception. So perception happens in our brain, not in our eyes. But it takes a bit of time. It's like information transmission. It takes time for the information to move from our eyes through the neurons to the visual cortex. And it takes about 1/10 of a second. I can hear you all say, well, that's not that much. It's not, but in neural terms, this is a massive delay. But more importantly, it's got huge implications for our perception. Because, of course, What does it mean if your brain sees the world a tenth of a second in the past? Well, we should be living in the past. Again, you might think, well, that's not that much. As I'm walking across this stage at this is about 1 meter per second. A tenth of a second delay would mean the world should be lagging about 10 centimeters behind me. And yet, it doesn't. Dave, catch. Amazing. That is amazing. Can you throw it back to me? Please applaud me, because this is probably one of the most amazing things that you've just seen. And I'm not being sarcastic, because, of course, these kind of things should be impossible. How can you catch a ball if you're seeing the past? Well, the only way we can actually compensate for this is by looking into the future. And what your visual system is doing every second of the day is it's using information from the past to predict the present. So what you're seeing as a now is not the now. It's your visual system predicting the now. Isn't that amazing? And so you are all literally seeing the future. Not loads, but a tenth of a second. That is still remarkable. And I said it was amazing, the fact that you could actually catch that ball. It truly is, because, of course, not only has the visual information already passed, but that doesn't incorporate all the time that is required for you to plan the motor action to be able to actually intercept this ball. And so all of our visual experiences are based on these clever tricks and heuristics and algorithms that the brain uses to solve these vastly complicated tasks. So why does all of this matter? Well, okay, magicians can use these kinds of tricks to fool your perceptual experiences. They can use these tricks to get you to experience the impossible, to experience things that simply shouldn't happen. But there's a much more serious side to this, because by using magic as a way of understanding the nature of human cognition, we are learning much more about a lot of these very surprising and often counterintuitive tricks. If the tricks would be obvious, we wouldn't be fooled by the magician. If you'd be aware of all of these tricks, you'd go, yeah, that was interesting, but I can't see these things anyway. Yeah, that's a cool trick, but my visual system is constantly being fooled anyway. It doesn't. The reason why magic works is because we are oblivious to these tricks. And understanding these shortcomings, shortcomings is the wrong way to describe them, because, of course, what it illustrates is just how clever your brains are at solving these immensely complex tasks. And this has got important implications for lots of areas. Think about technology. I've mentioned mobile phones, mobile phone use whilst driving. But think about technologies for the future. I mean, is it a good idea to develop human interfaces that allow you to present information onto glasses whilst you're interacting with the world? No, it really isn't. It might make intuitive sense because people are keeping their eye on the task, but doing so will distract them and they simply won't be able to see it. Most importantly, they're not aware of the fact that they won't see it. It's got major implications into the legal system or litigation. I've only talked about a few of these areas, perception, but of course the same applies to memory as well. So all of our memories are reconstructions of the world, and in the same way that our perception can be influenced, our memory can be influenced as well. And so just because you're remembering something doesn't mean you've actually experienced it. This has got implication for the legal profession. Litigation. Imagine someone who says, well, I was there, but I just simply didn't see it. You go, well, surely you're lying. No, he's probably not, because most of the things we're simply oblivious to. And so understanding these limitations, I think, has got really important implications for a wide range of areas in human life. If you're interested in this, I've just published a book by MIT Press called Experiencing the Impossible, which illuminates a lot of this. Very surprising insights that the scientific study of magic gives us into the human mind. Thank you very much.